All right, welcome. Thank you for coming. Glad to be here. This is a CQL overview. My name is Bryn Rhodes. I'm the Director of Standard Strategy at Smile Digital Health. I'm also a co-chair of the CDS working group that stewards the CQL specification. And I've been involved in this work for, I don't know, about 15 years now, something like that. So learning objectives. What is clinical quality language? How is it being used? And how does it enable knowledge interoperability? So we'll just start with a little bit of background. Why are we doing CQL? What is the point? And this kind of applies a little bit more broadly to also include the clinical reasoning module in FHIR, if you're familiar with that. The why is we want to reduce the development effort required for clinical systems to support evolving standards of care. There's a whole bunch of facets in that. How do we reduce duplicate effort while supporting innovation? How do we reduce inconsistency but still allow for setting specific factors? How do we reduce the accidental complexity involved in implementing systems so we can focus on the essential complexity of the really hard problem of keeping up with evolving standards of care? This effort takes many forms: guidelines, decision support measures, documentation templates, smart on FHIR apps, CDS services. There are some kind of ground principles that inform the approach that we've taken within the FHIR clinical reasoning space and clinical quality language in general. One is declarative versus imperative, so we want to talk about what we're doing, not how it happens. Separation of concerns, so keeping things focused on what their purpose is. Various types of independence, so independence from the physical implementation, independence from workflow and the case. And the history of computing, if you look at it, really is a history of raising the level of abstraction. So how can we raise that level of abstraction in this space? How can we look at what's happened across the industry and apply it to this problem? And one more is that we recognize there's no silver bullet. This is a hard problem, and there's a very large scope. So what we're focusing on is enabling the precise and unambiguous sharing of clinical knowledge. Especially with CQL itself, it's kind of its primary design purpose. How do we actually share clinical knowledge, clinical logic? So to get there, we start with talking about types of interoperability. So FHIR enables data interoperability, but there's a spectrum of interoperability, from data interoperability through to knowledge interoperability. And there are different types of interoperability within that get you to different points along that spectrum. Recognize this is not a discrete, this is a continuum. The lexical level means we're talking about the same symbols, so we're sharing the same symbols on both sides of an exchange. Syntactic means we're sharing the same structure of those symbols across, so we're sharing like the structure of a patient record or an encounter record. Then we get to semantic interoperability, where we're actually sharing the same meaning. So the same element on both sides of that structure, on both sides of that exchange, mean the same thing. And that's where you start to get into terminologies and sharing the actual meaning, and that's when you start to push into that knowledge interoperability. And then there's logical interoperability, where we're actually sharing, now that we have semantic interoperability, you can share a computation on that and know that on both sides of that computation, you're going to get the same result. And finally, process interoperability. If you can share your expressions, then you can start to share chaining those things together. These build on top of each other, and you can't really get to the next level without establishing the one below it. So CQL is focused on this logical interoperability. One of the ways that we kind of break down knowledge representation in this space is through knowledge representation levels. So knowledge level 1, you'll hear this referred to often as the kind of narrative, right? The guideline comes out. It's a 20, 30 page document. It's very dense. It's very domain specific. You have to have a lot of clinical knowledge to even interpret it. L2 gets semi-structured, so now we're talking about flow diagrams and decision trees, similar formats that are human readable and help to communicate between humans what's going on, but aren't necessarily to the level that a machine can actually interpret it. And that's L3 then, which is structured representation that can be shared of a computable representation of that knowledge. And finally, L4 is like running software in a system. So right now, things go typically from L1, maybe a little bit of L2, to L4. And that implementation effort happens in lots of different institutions all across the industry. That actual implementation typically can't share the result of that effort across different systems. The L4 effort is a siloed team that works to build, and it functions in their environment, but then they can't take that effort and transplant it to another space. That's the focus of L3, is to try to get an independent representation that can be shared across systems. So that takes us to what is clinical quality language. It's a domain-specific query language designed to represent and share clinical logic. So first, it's clinically focused. It has a bunch of constructs that support the expression of clinical logic, things like timing phrases and terminology interfaces. There are aspects of clinical logic that have representational support in CQL. 2, it's platform and technology independent. So it's a representation that it doesn't matter where you're running it or how you're running it. The conceptual representation of that logic is the same. It's also computationally complete. There are several different respects that it's complete. It's relationally complete, it's interval complete. And that's mostly to make sure that all of the different, because you can get to quite complex logic in clinical space, so the language makes sure that it's sufficiently expressive to capture those kinds of logic. And it's functional, meaning that you can't change values with it. You can only read values. You can only make computations from existing data. If you want to change data or save that data, that's outside the scope of CQL, and your system has to do that. It's a really important aspect of the language itself. It lends itself to implementations and translation and all sorts of goodies. So the specification is there, cql.hl7.org. It's a published mixed normative trial use specification, has been for almost 5 years now. And new this round is a CQL cheat sheet. I was hoping to have it all printed out and be able to pass things out, but the stars did not align. So that bit.ly should take you straight to the PDF. If you want to print it out, you can. But in that same folder where that cheat sheet PDF lives is a web-like markdown version of that. So a cheat sheet you can use for reference if you so desire. All right. So I'm going to take a little bit of a different approach. If you've seen me present on CQL before, we usually just like jump straight in and go through all of the things and talk about. What I'm going to do this round is come at it from a different perspective. So I'm going to start with decision support and how it's being used, and then drill in to what's actually happening. So for this, we're going to use a running example. This is the 2016 version of the U.S. Preventative Task Force colorectal cancer screening recommendation. Note, we recognize this was updated in May of 2021. It's an exercise for the reader to do that update. This link is to a repository that has this content that we're going to go through. There's also a detailed walkthrough if you're interested, and there's a VS Code plugin that you can use to open the repository, and it will give you the ability to execute the CQL and try it out and make changes and see whether it's working and all of that. So the narrative here, this is the L1, right? Appropriate screenings, colonoscopy every 10 years, flexible sigmoidoscopy, and so on. It's a pretty straightforward recommendation, but has a lot of detail in terms of the kinds of things that you can ask for and that represent evidence of appropriate screening in the case. So if you build the repository that's there, it's actually a FHIR implementation guide. And the things that are in it, instead of being profiles and structure definitions, it actually contains plan definitions, measures, libraries, resources that in FHIR represent knowledge artifacts like decision support rules and quality measure specifications. So you can share and publish those artifacts as a FHIR implementation guide, and that Colorectal Cancer Concepts IG is doing exactly that. So if you look at how you would actually use this plan definition, this decision support rule as a FHIR representation, this is where we take CDS hooks. So if you imagine an EHR on an order select, we're not gonna, this isn't, so I'm assuming some familiarity with CDS hooks. I hope that's okay. But in CDS hooks, as part of an EHR workflow, you're gonna generate a hook like order select. And that will fire a request to a service to evaluate some decision support. What's on the other side of that decision support is transparent to, or opaque, sorry, to the caller. All it knows is it's making a CDS hooks request and it's getting a CDS hooks response in the form of cards. So if you have a clinical reasoning implementation, what happens is the CDS hooks API request is handed to a plan definition, and that plan definition is applied to the patient in context, passed through with their data in that request. And that then evaluates the decision support in terms of the CQL. We're gonna walk down through what's happening here. And then that comes back. So the first thing is that we get the data, it turns into a plan definition apply, and that plan definition resource is effectively an event condition action rule. So one of the ways you can use plan definition is to say, when some event occurs, if some condition evaluates to true, then perform some action. So the plan definition references a library of CQL to actually say whether or not what to capture the expression. You see the has anemia is in this example. And then if that evaluates to true, then it creates the activity definition. In this case, it's a medication request for iron. So the colorectal cancer CDS rule, this is the rendering of that plan definition in that implementation guide that we're looking at. So the first thing is that it's got a reference to the library, that colorectal cancer screening CDS library. That's a library of CQL that contains the expressions to evaluate. And so the data coming in on the request is handed to the engine. It runs that expression, is recommendation applicable? And if that evaluates to true, then display the message, U.S. Preventive Task Force Services recommends screening for colorectal cancer. And this happens on the named event patient view. So when you're in a workflow and patient view fires, this comes in on a CDS hooks request. So looking at that, is recommendation applicable? So this is a library of CQL, and we'll go through this step by step and see what each of these things are. So the first thing is the library declaration. So the colorectal cancer screening CDS, that name is actually unique within your project. So in this case, that colorectal cancer screening IG, and that name is actually used to resolve it. So we take the base canonical of the IG, and we stick this name on it, and that gives then a globally unique identifier for this library. So now I can share this library anywhere because I have a globally unique identifier for it. It's got a version that's optional and is typically stamped with the version of the IG that you're publishing this thing with. Next is the model. So we're saying using FHIR version 4.0.1. CQL as a language is agnostic to the model. It doesn't care what kind of model you have. It just needs to know what the model looks like. So it can validate that when you ask for patient.gender, gender is actually an element of the patient. So each data model is described with a model info. That model info tells the translator and the environment what that data structure, what types are available in the model, what the primary code path is, so how you actually, we'll get into that on the retrieve. And it specifies the patient type. The reason it knows about patient type, this is a clinically focused DSL, and so the model understands what a patient is conceptually so that it can do things like calculate age. And then note, model info isn't required by ELM. It's only required to translate the CQL to ELM. All right. The next kind of bullet here is the included libraries. So we are including FHIR helpers, which is a set of functions that help you translate between FHIR types and CQL types. Mostly those happen automatically. But you can include any number of libraries by their version, optionally by their version. In this case, we have a colorectal cancer common and a colorectal cancer elements. And this called lets us say what we want to call this within our own library. So I've included colorectal cancer elements, and then I can reference it with elements as a qualifier. All right. And then expression definitions. So a CQL library consists of a set of expression definitions, and those expression definitions can then be referenced by things like the plan definition that's using it for its inclusion criteria, or a measure, or other libraries. If I include the library in a CQL library, I can call functions from that, functions and expression definitions. Which takes us to functions. So this is that age in years function. This is why the model needs to understand what a patient looks like so that it knows how to go ask for a patient's birth date so it can do the calculation to say what is your age in years. And that leads to then context, which is for a library, you specify what the context is. And from the perspective of that library, then, it's limiting the set of data that you have access to the patient that's passed in. In the case of decision support, that's the patient that came in on the request. So we're running a patient view hook for the patient in context in the workflow. And so we're evaluating then what the engine is doing right now is actually evaluating this is recommendation applicable. So it goes through, and when it hits this elements, it goes and now we're going to dig into the colorectal cancer elements library. So the first thing to note here is that we have expression references throughout. So anywhere that I can have an expression, I can call other expressions. This lets me build expressions up of any complexity in order to represent easily and clearly what I'm actually doing. So if you read this has appropriate colorectal cancer screening, it's very similar to the actual L1 representation here. But this is a formal L3 representation that can actually be shared and implemented consistently across systems. So exists fecal occult blood test within 1 year, fecal immunochemical test DNA result. So any of these returning true will return true for the entire thing. So let's dig into that a little bit. So that fecal occult blood test is actually itself a reference to fecal occult blood test result, where the issued is 1 year or less on or before as of. And that gets us to timing phrases. So within CQL and clinical logic in general, the temporal aspect is really important. There are all kinds of cases where what you care about is the relationship but from one data element to another in terms of time. Did this happen within 10 minutes of that? Did this happen during an encounter? Did this overlap a measurement period? It's ubiquitous in clinical logic to talk about relationships temporally. So CQL supports timing phrases that allow you to say those relationships in natural language. So I can say, does an interval start before or after? I can use starts or ends on an interval value to pick up the beginning or ending of that interval. So I can say things like interval X starts before the start of interval Y. And given two intervals, those will return true because the start of this X is before the start of Y. I can also say starts before, within, and offset. So I can say it starts 3 days before the start. And these will return true, and these will return false. Right? Starts 3 days or more before, and starts 3 days before. So I can actually pin it, or I can put it within a range. You can also specify a range for the boundary relationship using the within. So I can say that it starts within 3 days of, and all of these will be true because they're starting within 3 days, and these two outliers will be false. So those are timing phrases. All right, so the next thing is that when we got down to that fecal occult blood test result, we see this observation concepts, fecal occult blood test, FOBT. That's actually called a retrieve, and that represents data access within CQL. So anytime you actually need to go get data in CQL from the record, this retrieve is how you do that. And the retrieve has a type, and it has a terminology. The type comes from the model, so we're using FHIR, so we have a thing called observation. And the terminology comes from CQL declarations for terminology. So now we're going to talk a little bit about terminology. Terminology is ubiquitous in healthcare. FHIR has really good support for sharing terminology, doing expansion, supporting all different ways of communicating what the actual set of values are, and that terminology is the underpinning of the semantic interoperability. So if we have a code on both sides of an exchange, we have to know that we mean the same thing. And so terminologies are where we get that. If you look at the colorectal cancer concepts IG, it has a specific library dedicated to just declaring and supporting the concepts that are used. That way we keep the concepts that we need in our logic and the declarations associated with that separate from the logic. CQL supports code systems, value sets, codes, and concepts. It does not define them. It only supports the reference to them and the name for a local identifier that you can use within your CQL to talk about that. So if you look at this value set colonoscopy, that's actually a reference to a value set that in this case is housed in the VSAC, Value Set Authority Center, a terminology service in the US, supports various CMS program initiatives. But this URL could be any valid FHIR URL. And to CQL, it doesn't care, it's just a string. And all that means is this is a stand-in for that URL. So when I say colonoscopy in this library, I'm talking about that value set. Terminology identifiers can be statically bound to a particular version, or you can leave that version reference flexible. And there's a whole kind of session and talk about CRMI, where we'll get into more about that problem. Just know that best practice typically is to leave that version unspecified in the CQL. And then you, as you distribute, you actually specify the version as part of the package, not part of the source content. CQL has a code structure. This is basically the same structure as a FHIR.coding, code, display, system, and version for an actual code in a code system. And then it has a concept, which is analogous to FHIR's codable concept, which is a list of codes that lets you specify equivalent codes representing the same concept. And this is one of the really important ways that we get interoperability, by allowing multiple code systems to specify the code for a concept on both sides of the exchange. They can keep their local identifier, but they can also provide a standardized identifier for that, as well as a display. So there's some examples there of code system Loink, a code from that Loink code system, and a code system SNOMED CT. So terminology operator, CQL has, in addition to being able to talk about the terminology, there are specific operators for terminology operations. So string valued codes are only used for required bindings. So I can say o.status in final or amended, because the status element of the observation resource is bound required to a set of codes. So I know if I'm looking at observation, the only possible values for that status are final, amended, corrected, as listed in the spec. So this is the only case where it's okay to use an actual string value there and construct a list like that. Because there is no system, right? It's implied by the binding. Use inline value set only for required bindings and only with string codes. So I can say o.status equals final, or I can say o.status is in that list. So these braces are list selectors. Use in to test for value set membership. So I can say where the value is in current smoker. So most recent smoking status observation. This value is expected to be a code, and this current smoker is a value set, and that will be a value set membership test. This isn't the same as a list in, because what's happening is we're actually asking if that code is in the value set. If it's a codable concept, then any coding that's in that value set will return true. If it's just a code, then it will be a code in that value set. And the key difference is the code equivalence is what's being used to determine membership. So we'll note this is not terminological equivalence. It's not doing anything with the code system properties or hierarchies or subsumption or anything like that. All it's doing is saying the codes on both sides have the same code and system, ignoring the display and version. So this tilde operator is the equivalent. And so if you want to test for a value being equivalent to a code, you use that tilde. If you really, really mean, is this the same code and the same version and it has the same display, you can use the equal operator. But in general, for terminology equivalence and comparison, use the equivalent operator. Okay. All right, so that's terminology, end of aside. Now we're going to go to data access. So we're inside a retrieve. We're asking for observations of a fecal occult blood test. These slides are for observation of tobacco smoking status, but it's the same idea. In CQL, what we are describing in the expressions is conceptual data access. How that physical data access actually happens depends where that CQL runs. So remember, the point of CQL is to be able to take logic and run it wherever you need to express that. That might be part of a decision support rule, like we're in the middle of right now, evaluating a decision support rule. Or it might be in a quality measure, evaluating across an entire population, or it might be in a public health report. How that actual physical data access occurs is an implementation concern, not a language concern. And CQL is silent about what that means, where that data actually comes from. All we know from the CQL perspective is that evaluation of this expression requires observations in the tobacco smoking status value set. So we call that a data requirement. If we're in process, we have an actual engine and it has access to local interfaces to get data, then the engine can actually access the database directly. We call that in-process data access. If we're out of process, we're running remotely, that actually might be a service access. So this might, that requirement to get observations in the tobacco smoking value set might actually be a call to a RESTful FHIR endpoint. And so it would turn it into a FHIR API query and go ask for that data. It might be prefetched. In the case of CDS hooks, one of the features of that specification is that a service can advertise its data requirements. It can say, in order to run successfully, I need observations in the tobacco smoking status value set. And so please provide that data, because if you don't, I'm going to have to go get it anyway. And so the prefetch has a way for the CDS hooks request to have the client pass that data as part of that request. And so the engine then is accessing that passed in data. That's another mechanism for getting data to the service, to the engine. If you look at the reference implementations, this idea of getting to the data is actually abstracted through a provider interface. And depending on where that engine is running, it might be running on your phone and getting data from the phone's local store. It might be running in a service and using a FHIR endpoint. But all of that data access is happening behind this provider interface. So to the engine, it doesn't care. It just knows that it's going to call this interface, get data, and then deal with that data. Which leads then to that context, where we said the context is patient. The data access layer is where that context really comes into play. Because at the data access layer, what you're doing with the context is providing a filter on the data that's accessible, sort of like compartments in FHIR. You have a context unfiltered, which basically means you can see everything, versus context patient, which means you only, when you ask for data across a retrieve, you only get data for that patient. So when we ask for observations in the tobacco smoking value set, we're only going to get the observations that have a subject of the patient in context. All right, end of aside. So next is FHIR queries, CQL queries. If you look at that fecal occult blood test result, it's taking the observation concepts fecal occult blood test, and it's giving it a name. We call that an alias, and that's starting a query. And as a language construct, that means then that you can introduce clauses. In this case, we're doing a where clause, and we can use that alias to access. You can think of it as, if I have a list, then it's going to execute that against every element in that list. And the where clause is only going to return from the expression elements in that list that evaluated to true for this condition. So the result of this is observations in the concepts fecal occult blood test, where the status is in final, amended, corrected, or preliminary, and the value is not null. Query clauses, so there are several. We can introduce local variables within the query clause using a let. We can relate that source to other sources. So I can say, give me observations that occurred during an encounter using with and without. There's the where clause and that we just talked about. And then I can also sort. So I can give that data back in any particular order. So next up is functions. I have 10 minutes. Okay, good. I might need to speed up. All right. Colonoscopy performed within 10 years. This is another one of the data elements in that has appropriate screening. What's happening here is I'm getting the most recent colonoscopy performed by calling this most recent function. And so in CQL, I can define functions. They take a list of arguments. And within that function, I can reference those arguments to do things like give me the first procedure where the interval starts or the interval ends on or before the as of, and sort by the start of the performed interval. So then that most recent function, I can run that on any list of procedures to give me the most recent procedure. And I use that throughout. Now, one thing we want to call out here is the performed element in a procedure in FHIR is represented in any number of possible ways. It can be a single date, it can be a range, it can be a string, an age, a period. And so if I'm in that logic and I want to know whether the performed ends 10 years or less on or before, I have to account for all those different possible ways that the data might come in, because the FHIR resource lets me represent that. Part of that is profiling, where you might have a profile that limits the set of possible representations there. But in general, you need to account for all the possible representations that are coming in. So CQL has a case statement and a choice type. So those elements in CQL are represented as choice types. And this fluent function, that's a little bit of an eye test, but what's happening is it's going through each of the possible representations and returning it as an interval. So if it's a date time, it returns it as an interval of starting and ending on that same date time. If it's a period, it turns it into an interval. And this is what we call a fluent function in CQL, which means that I can invoke it on the first argument using a dot. So what's happening in this performed .to interval is I'm actually calling that fluent function, and that's effectively inlining that whole expression so that I can, with just by saying to interval, I can account for all the different possible representations of that performed. And because I can define fluent functions myself, I can do this with any kind of logic that I want to package up and put into a nice simple representation like that. So that performed .to interval is actually hiding some fairly complex logic that even takes into account the fact that the performed might be represented with a duration since the patient's age, right? It'll actually go calculate, if that's the case, it'll go calculate the patient's age and determine the within 5 years or whatever. So that's a fluent function. Now we're going to pop back out. So we just evaluated that recommendation applicable. We're going to come back up. So is recommendation applicable returned true, let's say? Then what, right? What happens where we're popping back out? This is another eye test here. But what's happening is we're taking all of those components and getting the most recent one, and then using this coalesce operator. So coalesce takes any number of arguments, and it'll pick the first one that isn't null. And so if the reason you have appropriate screening is because you had an FOBT or fit DNA or colonography, it's going to pull whatever one comes back first. So what we're doing here is constructing the rationale for the recommendation that we're making. Patient meets the inclusion criteria for appropriate colorectal cancer screening, but most recent FOBT was issued before the actual threshold, right? So what we're doing is collecting the evidence that we're using to make this decision so we can display it to the clinician as the rationale for this recommendation. And you'll also notice, I got 5 minutes, we've got the card summary, card detail, and card indicator. These are expressions that are then going to be provided back as the values in the response to the CDS hooks request. So what happened there is we evaluated, we went all the way down, we came back up, and what we're doing then is turning the values of the results of those expressions into the CDS hooks response. And that's reasoning as a service. Let's look at quality measurement real quick. That's 5 minutes till the end of the session, right? Is it 5 minutes till the end of the session? Okay, I'm gonna jump through here. So also in that IG is a quality measure. This is the rendered version of that quality measure. You've got an initial population, denominator, and numerator. Basically, it's the proportion of patients that had appropriate screening. And the key here is that we're using, in the numerator definition, that same elements dot has appropriate colorectal cancer screening. So on the decision support and the measurement side, I'm actually using the same logic to get to that result. So then this is the slide that I usually start with, where we talk about, so we've talked about decision support, we've talked about quality measurement. This is a representation of the quality improvement ecosystem where data is coming in through research, synthesized to clinical practice guidelines for best practices, operationalized through clinical decision support at the point of care, and then we use measurement and analytics to determine what happened, and public health reporting and quality reporting to agencies that care about that. And ideally, this forms kind of a learning health system, a virtuous cycle, continuous quality improvement. All of these are specifications that are related to supporting the exchange of knowledge artifacts across these different points. So quality measures and how you report on quality measures and how you represent decision support and how you call it with CDS hooks, how you represent a computable guideline with CPG. And places that CQL is currently being used with those implementation guides, quality measurement and reporting, public health reporting, CDC opioid guideline, which there will be, I think that's later today, a discussion or a session on the opioid guideline as implemented in the CDS hook sandbox. So some updates there. WHO guidelines through an initiative there, and there will be a talk tomorrow where we're talking with about that initiative. And you can find and reach me at any of these things. If you want to learn more and or get involved, the VS Code plugin, there's a user's guide there. Just walks through how to use the VS Code plugin so you can open it on any IG and start executing CQL, building test cases, getting the results. Cooking with CQL monthly sessions. We do a monthly session. You can, it's open to anybody. We've had this is 85, I think, is coming up. So we do this every month. We've been doing it for years. There's the Zulip CQL stream where we support community questions. And if you want to come help with vNext of CQL, that's the clinical quality language project page in the clinical decision support workgroup. And I'll be talking a lot more about what that CQL vNext looks like on Thursday with the future of CQL. 1 minute for Q&A. Sorry, that was a lot. I tried to reverse it. I tried to do it in a totally different way than I usually do. So hopefully that was helpful.
Question, and probably be a while before Mike gets to be the guy. Go ahead. Could you just speak briefly to how the data requirements piece for computing that, well, where that's going and evolving? I think that that's a real part of the challenge, right? Is getting the data to the execution and having the authors be able to kind of really specify what data they need. I'm familiar with the data requirements piece that can come out of it, but how nuanced that is and how the authors can kind of tune that or add to that. Is that something that should be generated automatically? Is it something that should be the author should be able to edit? Can you just kind of give your thoughts off the top of your head on that?
Right now it's generated automatically, and there are some different options you can provide. There's like an analyze data requirements and a collapse data requirements. What it'll do is go through and pull all the requirements out, but it'll also do things like try to look for restrict optimizations, like push down, so it can actually, if you've asked for a date range, it can actually push that inside the requirement. But all of that processing is fairly complex, and so that all happens as part of the refresh right now. There's a refresh that goes through and does all that computation. We're looking at ways for authors to make that more, kind of make it more part of what they're able to do and talk about, but also ways that an implementation can tune what those data requirements are and how they match their, because it's really the kind of query optimization piece, right? And so there are extensions like isSelective that you could put on a data requirement to say, this is a selective requirement for this. So you could actually, from an implementation perspective, you could take just the selective requirements and run just those, and then that gives you a superset of the data that the actual CQL needs. So it's an area of active effort. There's a lot going on there, and we're trying to get that to be flexible, but also as automatic as possible. So, great question. All right. Thank you. Appreciate it.